Hi. In this video, we are going to start a new subject, which is called first-order differential equations. Okay, in this video, I'm just going to show you how to solve the most basic differential equation, and we're going to introduce a lot of new terminology. But I'm going to be doing this very slowly. Okay, so first, what is a differential equation? Look, differential equation is an equation in which we have a derivative. And when we find a solution, we need to get rid out of this derivative. And normally, it could be very problematic, but at this moment, we have established a certain ways in which we can easily find solutions to different types of equations. Okay, so what we are going to deal with in this part of the class are first order differential equations. What does it mean first order? Well, first order just means that we will have only first derivative in this equation. And look, second order differential equation is going to be an equation that has first and second derivative or just second derivative. Third order differential equation would be an equation with third derivative. And look, even if we have just third derivative, it is already third order differential equation, even if it doesn't have any other derivatives. So basically, the order of the difference equation the order of a difference equation is defined by the highest derivative. If the highest derivative is third derivative, it's third order. If it's second, it's second order. And of course, we're going to start with first order differential equations. Okay, and look, we also going to deal only with so-called linear differential equations, or in other words, of differential equations of the first degree. Okay, so let me show you how equation like this looks. So here we have dy dt. So this is first derivative of y with respect to t plus some function t times y, which is also a function of t, and equals to wt. And this is first degree differential equation. And look, I know that usually when you heard the word linear, it means that we will have just coefficients. But look, here we can have a function, some function of t. It can contain constants, slope, some t times slope, t squared, doesn't matter. It's still a linear equation because look, what we actually have here is only the first derivative, the function, and two functions of t. Any of these two functions of t does not contain y. Now look, for example, if we would have equation like this, this is still first order differential equation. Why? Because look, we still have first derivative. The only difference is now that this first derivative is taken to the power of 2, which will tell us that this is second degree differential equation. Okay, and look, we are going to be focusing only on first degree differential equations, and we will just do a couple of extensions, but only for those simple cases and those cases that we use in economics. Nothing too complicated. Now, look, the first case that we're going to do is the simplest possible differential equation. And unfortunately, look, it has a long name, but as you will see, it's easy to remember. This is going to be first order but also first degree differential equation with constant coefficient and constant term. Okay, so how does the equation like this look? Okay, this equation will look like this. We will have y dy dt plus a times y equals to b. Okay, so now the question is, how do we solve it? Look, but maybe let's first look at some things. In this equation, we have constant coefficient and constant term, which means both a and b are a given number. They are constant. And as it turns out, in these circumstances, solving those equations is relatively simple. Okay, but how do we go about in solving such differential equations? Well, we usually, when we want to show how to do it, we usually start with homogeneous equations. So, homogeneous case. Okay, I hope you remember from mathematics that generally homogeneous equation is the equation where constant term is equal to 0. So look, homogeneous differential equation will look like this. dy dt plus ay equals to 0. And look, actually, even without any additional knowledge, just using what we already know about the integration, we can figure out an easy way to solve this differential equation. Well, what would we do first? Well, first probably we should take this on the other hand side of the equation. So we get dy dt equals to negative ay. Okay, what would we do next? Well, what I would do here is I would divide both sides of this equation by y. And look, what we get out of this is that we've got 1 over y dy dt equals to negative a. And look, what are we getting out of this? Look, expression that you see over here is nothing more than the growth rate of y, right? Because this is derivative of y with respect to time, which we also know now. Then we can write like this, divided by y. So this is growth rate of y, and look, we see that we have constant growth rate equal to negative a. So, but remember, a can be both positive and negative, so it could be growth or it could be decay. Now, can we remember from our mathematics class or our previous considerations in this class, when do we have a function that has constant growth rate? Well, this function is the function with e, right? Look what we were doing before. When we differentiated expressions with e, we were finding that r standing next to t in expression e to the power rt was our constant growth rate. So look, we are actually expecting that somewhere along the way we should get e over here, and this is actually what we're going to do. What is going to happen? But of course, this even though we can suspect this, at this moment we can resort to more mechanical tools. Because look, if I want to here find y, and I have the derivative, what should I do? I should use an integral, because if I'm going to integrate derivative, I'm going to get a function. And look, so what am I going to do here next is that I'm going to calculate integral of 1 over y dy dt dt. But now, of course, I need to do the same thing on the other hand side. Okay, so what are we going to get out of here? Look, what would we see in this case is that we have derivative divided by the function. So clearly we need to use logarithmic rule. And look, this is what we are getting over here. We are getting that this is equal to ln y equals plus c, of course, let's call it c1, equals to, of course, an absolute value, because we do not know whether y is positive or not. And over here, we will get simply the integral of this, which is negative a times t plus some c2. Okay, and not to complicate things too much, we know that this is an arbitrary constant and this is an arbitrary constant. We don't know how much they are. So let's just replace them with one arbitrary constant, and we will have just negative a t plus c. Okay, and now look, here is where situation complicates slightly. Look, because we have absolute value of y, we can consider two cases. Look, if y is bigger than 0, then this equation turns into ln y equals to negative at plus c. On the other hand, if y is lower than 0, we will have here ln negative y equals negative at plus c. And look, I'm going to show you the solutions for both, and you will see that actually we are going to end up in a very similar situation. Oh, maybe I should write it like this, I'm sorry. But of course, these are parentheses, not absolute value anymore. And but look, when we deal with economic problems, y is price, it's quantity, it's GDP, it's consumption, it's investment. Those are the variables that do not take negative values. So we will concentrate on what we're going to get over here. Okay, so let's start solving this. Look, here we want to solve this for y. So we see here that y is in logarithm. So in circumstances like that, we use something called anti-log. I was also showing you this in mathematics class. How does it work? Look, I'm taking e, and I'm simply putting this as a power of e, and this part as a power of e. Okay. Okay, and why is that convenient? Because look at this expression. We also seen it in mathematics class, but look, natural logarithm asks us a question, to which power I need to take e to get y. And look, so the solution to this is some power to which, if I'm going to take e will turn into y. So what am I going to get over here? I'm going to get here y. Okay, what's on the other hand side of the equation? Look, here there's not much more that we can do. Not much more than we can do, but one thing that definitely we can do is we can take this plus c and make it into a separate expression, okay? We will have it like e to the power of c times e to the power negative a t. And look, from this moment on, because look, we don't know what c is, we do not know what this number exactly is as well, right? So what I'm going to do over here is I'm going to simply replace this e to the power of c by capital letter A, and here we will notice that a is equal to e to the power of c. And let's notice one simple thing, that in this scenario, of course, a is going to be bigger than 0. Because look, it doesn't matter to which power I'm going to take e, I'm never going to get 0. Right? Okay, look, this is actually the solution that we're going to be using. It is called a general solution. But before we introduce a little bit more terminology to this, let's solve the other part of the equation. Okay, so how do we deal with this one? Well, in a very similar way. Again, I need to take anti-log, and as a result, I'm getting e to the power ln negative y equals to e to the power negative a t plus c. And look, we will use the same trick here. So I'm going to get negative y over here. And over here, I'm going to do the same trick as before. So I'm going to put e to the power of c up front times e to the power negative a t. Okay, and now look, the only one other thing we would have to do over here is to take this minus to the other hand side, because we want to solve this for y. And again, I can just replace it with the constant a. And now our constant a is equal to negative e to the power of c, which is clearly lower than 0. Okay, so we've actually obtained the formula that gives us the solution to this differential equation. And look, this, okay, so one important thing to remember is that when we solve a differential, when we are solving a differential equation, what we want to obtain is called a time path. What is a time path? Look, time path is a function that is expressed solely in the terms of t. So we've got y over here that is only a function of one variable t, and the solution is given by a to the power e negative at. Okay, this a we will call an arbitrary constant. Oh, maybe I'm gonna write it, but just like in case of integrals. So look, we don't know what is the value of this constant, right? This is why this type of solution is called general solution. Now, if we know some additional information about the problem we are dealing with, we are very often given something that is called initial condition. And this initial condition is some y of 0. Look, y of 0. Look, it's like let's imagine that we are starting our analysis from some point in time, right? So time is going over here, right? And we are starting at this point. And we are not interested in what was happening over here. So we can assume that we are starting at some point 0. And in order to find the appropriate solution, we need to know what was that value of the variable of interest at the very beginning, right? Look, it's just like with integrals. We've got arbitrary constant, and sometimes we need to have some additional information in order to find appropriate solution. Look, when we were talking about integrating marginal functions to get total functions, this is what we were doing. When we were dealing with marginal cost, we needed to know what is the fixed cost. When we were dealing with marginal revenue, we needed to take the use of the information that total revenue is equal to 0 when quantity produced is equal to 0. And this is going to be very similar over here. So this y0 we are going to call initial condition. And once we know what is this initial condition, we can replace our A with this initial condition and then we will obtain something that we're going to call definite condition, the definite solution. Okay, so in other words, the process of introducing initial condition into differential equation is called definitizing an arbitrary constant. Okay, I know that there's a lot of new terminology, but look, as we will move on, you will see that actually we're just gonna need 2 to 4 different expressions because we will be dealing with very specific economic cases, and now we are just learning how to do it. Okay, but this is so what we have accomplished at this moment. Look, at this moment we have found a solution, but to a homogeneous equations, right? With homogeneous equations, remember, we need the one in which b is equal to 0. And look, this is not a very interesting case because it gives us just one of infinite number of possible cases where b can be a different number. So in the next step, what we need to do is to deal with non-homogeneous case. Non-homogeneous case. And non-homogeneous case is the case where b is different than 0. Okay, so now the solution to the full equation, or we can say the full solution to this equation will have two parts. The first part we're going to call complementary function. And we denote this complementary function by yc. The second part is going to be called particular integral. And we denote it as yp. And look, if we have a complementary function and particular integral, both of them, when we simply add them, are going to give us the solution to any differential equations. Okay, but before we get into complementary function, what is complementary function, in particular integral, let me just introduce a couple of different notions. Look, very often homogeneous equations is called reduced equation. Look, why is it like that? Look, think about it. Because non-homogeneous equation is simply there's only one difference between homogeneous and non-homogeneous equation. This b. So if I would just take this b out of non-homogeneous equation, I would get homogeneous equation. So this is a reduced equation. And look, by the same token, we can say that non-homogeneous equation is complete equation. Complete equation. Okay, and if once we realize that this is a complete equation, because it's like you take the homogeneous equation or reduced equation, you add the missing constant term or variable term later, and you obtain complete equation. Okay, so knowing this, we can write the proper definition of what is complementary function. Okay, so what is complementary function? A complementary function is a general solution to reduced equation. what is particular integral? Particular integral is any particular solution to the complete equation. Okay, and look, this information over here is very important to us, because look, now that we know that complementary function is just general solution to the reduced equation, it means that this general solution that we've obtained will not only work for homogeneous case, but it also is going to work for non-homogeneous case. But in non-homogeneous case, we need a little bit more, right? Because thus far, we've got just complementary function. We need to also find particular integral. But let's again look at the definition of the particular integral. This is any particular solution to the complete equation. And look, this is a very important information, because if this is any if this is any solution, then we should not try anything complicated. We should try the easiest solution that we can find. And this is what we're gonna do. Look, what is the easiest solution we can find? Of course, it's a constant, right? So look, we would assume, and we would consider this case, that y of t is equal to k, where k is a constant. Okay, why solution like that? Look, first, because it's easy. Second, what does it mean? Look, it means that y is not changing over time. That would be tempting, definitely, because how easy that would be. And look, again, here we see our differential equation. And look, if y is equal to k, then dy dt is equal to 0, right? Derivative of a constant is equal to 0. So look what happens over here. Now, if I'm going to take this non-homogeneous equation under the assumption that k is equal, that y is equal to some constant k, then this part is gone, right? Look, the only thing left we've got is ay equals to b, right? So now, how much is y? Y, and we can write already yp, is equal to b over a. So, now that we've done it, we can actually write general solution to the non-homogeneous differential equation, and this general solution is, of course, y of t. Remember, we call it the time path because this is going to be function of time alone, and it's equal to a times e to the power negative at plus b over a, right? We just added complementary function to particular integral. And look, those are the two terms that I'm going to be using all over until the end of this class, over and over again. So those are the two terms you need to remember. Each of them has a very specific interpretation from both mathematical point and economic point. But you know, I'm going to wait with the interpretation of this until we actually do one economic problem, because now, if I would start telling you now what they mean, it would just confuse you and it still would seem weird. For now, we're just going to focus on mathematics, and once I'm going to introduce economic problem, you will see how easy and pleasant are interpretations of these two components. Okay, but look, this is just general solution. General solution means we have an arbitrary constant, because look, B, A, and A are the things we already have had in the equation. So they are not anything new. A is something that we got in the process of solving the differential equation. So look, again, we need to definitize this arbitrary constant. Okay, so how do we do it? Look, it's actually really easy. Again, we're going to use initial condition. And look, initial condition is that we know what is the value of y at some point of 0. But look, if y is 0, what is happening over here? We get that over here we've got a times e to the power a, negative a, times 0, right? Plus b over a, which gives us 1, right? Because e to the power of 0 is 1. So we've just got a plus b over a. So look, we know now that y0 is equal to a plus b over a, and consequently a must be equal to y0 if I take subtract b over a from both sides of the equation minus b over a. And this is something we can substitute back into the general solution and obtain definite solution to non-homogeneous equation. And this definite solution is equal to y of t. Remember, this is a time path. I'm going to probably be repeating this to you very often. And look, usually open brackets here, and we've got that this is y0 minus b over a. Again, you will see that this has very nice economic interpretation, as well as a generally mathematical one, times e to the power negative at plus b over a. And this formula gives you a definite solution to non-homogeneous differential equation. Okay, now let's do a couple of examples before we start. Oh, you know what? One more thing about particular integral before we move on further. Oh, no. Let's stick with this. I'm going to start with this in another video, in the next video. Okay, let's just do a couple of examples. I don't want to keep this too long. Okay, so let's just say that the equation we need to solve is dy over dt plus 2y equals to 6, and we know that our initial condition is that y at 0 is equal to 10. Okay, look, we are not going through the entire process that I've just shown you. We just use the solution. Look, and first, let's just find general solution. Well, general solution tells us that y of t is equal a to the power e negative 2t, right? Because we just need to take whatever constant is here, put minus up front, and right next to t. And then we've got plus 6 over 2, because this is 6 over a, which is to b over a, which is equal to 3. Right? Then the definite solution is going to look like y 0 minus 3, right? Because we subtract the same number that we've got over here, times e to the power negative 2t plus 3. And look, we solved this equation. Again, I know that for now we're just practicing math. Later on, we will do, once we're gonna get to economic example, we're gonna concentrate on their interpretations. Okay, let's just do one more example, and I think this is it for one video. Okay, so next example is actually with homogeneous equation. So we've got dy dt plus 4y is equal to 0. And we've got the y 0, so our initial condition is 1. Okay, this case is even simpler than the previous one. Let's start again with general solution. So we've got the y of t is equal to a times e to the power negative 4t, and that's it. Because this is homogeneous equation, we do not have particular integral, right? And also this means that in our case, the definite solution is just, we substitute a with 1, so we've got just e to the power negative 4t. Okay, and let me just bring your attention to one detail. Look, in the formula for particular solution, a particular integral, we've got that b is divided by a. And look, if b is divided by a, this means that a must be different than 0. Right? In both cases. But what if a is equal to 0? Well, this is going to be the topic of our next video. Take care.